Hello everyone! What we're going to be doing today is going through all of the multiple choice questions on OCR's modeling physics paper from June 2018. Probably the best way to watch this video, if you haven't attempted the questions just yet, would be to just pause this video before I've started the solution, attempt the questions yourself, and then check with my answer. So let's get started. Question number 1. Which of the following units is not an SI base unit? The amp, well, that's a base unit. The mole, that's also a base unit. The volt, definitely not. And the kilogram is. So remember, there's only a few base units and you need to know all of them. And if you haven't watched my base units video, please scroll through the channel and you'll be able to find one. So the correct the correct answer for this one is C. Which set of quantities are all scalar? So remember, a scalar quantity only has a magnitude rather than a direction. So going for the first one, acceleration. Well, acceleration definitely has a direction, so this is a vector. In fact, all of them from part A are vectors, so it's not going to be this one. B, energy, this is a scalar, mass is also a scalar, and power, that's just energy over time, so that's also a scalar. So this has got to be the correct answer. Just for completeness, for part C, the vector is a force, so it's not this one. And for part D, weight is also a vector, which is pointing in a particular direction. So just like that, the correct answer is B. Okay, moving on to question number 3. We have a metal block of mass 0.28 kg with initial temperature of 82 degrees C, and that's dropped into cold water. The temperature of the block after 1.2 minutes is 20 degrees Celsius. We've got the specific heat capacity. What is the average thermal power transferred away from the metal block? Okay, well, we know that power is in general energy over time. So let's just rearrange for the energy, and we know that energy is power multiplied by time. Now we know the left hand side of the equation, that's going to equal mc delta theta, and it's going to equal to power multiplied by time. This is the left hand side is just the specific heat capacity equation. I have a whole separate video on this if you want to explore the channel further. Now because we're looking for power in this case, all we need to do is rearrange for the power, and this is going to equal to mc change in temperature divided by the time. And now we can start plugging in some values. So we know that the mass is 0.28 kg. We know that the specific heat capacity of this material is 130. Our change in temperature is 82 minus 20, so that's 62 degrees. And finally, our time is 1.2 minutes. Minutes is not an SI unit, so I'm going to have to convert that to seconds. In fact, I'm going to do that in a different color because this is really important. Please don't forget to do this in an exam situation. So it'll be 1.2 divided by 60. Now if we plug those numbers into our trusty scientific calculator, we're going to get approximately 31 watts. So correct answer is A, 31 watts. Right, question 4. The acceleration A of a simple harmonic oscillator is related to displacement by the following equation. What is the frequency of this oscillator? Okay, well, the equation that relates simple harmonic motion and its acceleration and displacement is acceleration is minus omega squared times x. So we can see here that omega squared is equal to 25. We know this because the equation which we're given is minus 25x like that. So it means that omega squared has got to be 25. Now this means that omega is going to equal the square root of 25, which is 5. And what we're going to do then is just remember that omega actually equals 2 pi f. So omega equals 2 pi f. So 2 pi f multiplied by 5 is equal to 5, excuse me. So it means that the frequency will just be 5 over 2 pi, and if we put that into our trusty scientific calculator, we're going to get about 0.795. Oh, that's a few too many significant figures, so correct answer is A, 0.8. Question number 5. A rod is fixed to a pulley. 250 Newton forces are applied to the ends of the rod as shown. The tension in the rope attached to the pulley is T. The system is in equilibrium. Okay, well, the first thing we need to note is if the system is in equilibrium, that means that the sum of the clockwise moments is actually equal to the sum of the anti-clockwise moments. Which one of these moments are clockwise? Well, this 50 Newton one, that will move this rod in the clockwise direction, so that's clockwise. I'm going to write a little CW here. The other 50 Newton one is also in the same direction, so that's clockwise as well, because they're both attempting to turn this sort of in the clockwise direction. This tension though, that's actually attempting to pull it in the opposite direction. Okay, well, because the principle of moments actually says that the sum of the clockwise moments, so let's just write that, so all of the clockwise moments, it has got to equal the sum of the anti-clockwise moments. The only force which is providing us with an anti-clockwise moment is actually T. So let's add all of the clockwise moments first of all. We're going to start off with this 50 Newton force over here, so that's 40 centimeters away from the pivot point. So it's going to be 50 multiplied by 0.4. Okay, and plus another one of exactly the same, because this is also a force of 50 newtons, which is 40 centimeters away. So it's going to be 50 times 0.4 again. That's going to equal to the anti-clockwise moments, and the sum of the anti-clockwise moments, there's only one, and that's the moment of T. So I'm going to call that sort of MT for short. Well, if we just calculate that, we will instantly have our moment due to force T. And okay, so this one here is 20 plus another 20. This is going to be 40 Newton meters, like so. Notice over here, this is not looking for the force T. It's looking for the moment of the force, which is what we have found out. So the correct answer is D. Okay, question number 6. The latent heat of a vaporization of a liquid is 2,300 kilojoules and has a molar mass of 0.018 kilograms per mole. What is the energy required to change 30 moles of the liquid to a gas? Okay, well, the formula for the specific latent heat, or the is essentially that energy is equal to the mass multiplied by the specific latent heat of vaporization. Now we know that the specific latent heat of vaporization, that's given in the question, so all we need to figure out is what mass we're dealing with, and we are in business. So if you remember from my number of moles video, then we know that the number of moles, so number of moles is given by your mass over the molar mass divided by the molar mass. So in this case we have the number of moles, that's 30. We have the molar mass, which is 18 grams per mole, so we can just calculate the mass. So the mass in this case is going to be the number of moles times your molar mass. So 30 times 0.018. That's going to be your mass. And so if we multiply those two together, we get 0.54, like so. And right, what we can do then is to multiply those out to get the specific latent heat, or the energy, sorry. So let's calculate those out. So the energy is going to equal to the mass multiplied by the specific latent heat. So our mass is 0.54 kg multiplied the specific latent heat. which is 2,300. So they're kilojoules, so I'm going to multiply this out by 10 to the power of 3. And if we put that into a scientific calculator, we're going to get 1.2, approximately 1.2 multiplied by 10 to the 6 joules. So the correct answer is B. Okay, question number 7. So we have one end of a spring is fixed and force F is applied onto the other end. The elastic potential energy in the extended spring is E. The spring does obey Hooke's law. What is the extension of the spring? Okay, well, let's start off with just writing out a formula for the potential energy of a spring. So that's equal to a half times the force applied times the extension. This is given in your formula sheets. So we can just simply rearrange for the extension x. So in this case, x is equal to 2e divided by f, and so that leads us to answer C being the correct answer. Question 8. An electron makes a transition between two energy levels as shown. The transition produces a photon of frequency 4.1 times 10 to the power 14. What is the value of the energy level x? Okay, well, let's calculate the energy of that photon. As you remember, E is equal to hf, which is equal to Planck's constant, which is 6.63 multiplied by 10 to the power of minus 34, multiplied by the frequency, which is 4.1 times 10 to the power of 14. Now what we need to do next is we need to put those into a scientific calculator. So let's do that. 6.63 times 10 to the power of minus 34 multiplied by 4.1 times 10 to the power of 14. So that's going to give us 2.71 or 2.72 multiplied by 10 to the power of minus 19 joules. Okay, so this is how much energy was lost. So we need to take that away from this energy level over here. So minus 5.4 multiplied by 10 to the power of minus 19 minus 2.72 times 10 to the power of minus 19, and when we take away those two numbers, we're going to get approximately minus 8.12 multiplied by 10 to the power of minus 19 joules. Okay, so the correct answer is D. A good useful rule of thumb to remember is that as you go down, the energy becomes lower and lower. However, higher negative number actually means a lower amount of energy. Okay, question number 9. A pendulum is oscillating in air and experiences damping. Which of the following statements are correct for the damping force acting on the pendulum? So number 1, it is always an opposite in direction to the acceleration. This is actually incorrect. The reason why it's incorrect, if we imagine this pendulum over here that we have here on the right, if the pendulum is going over to the left, in fact it's slowing down, but its direction of motion is opposite. So that means that the damping force, let's call it D, is going to be acting along this way, but because it's slowing down, the acceleration is also acting in the same direction. So the first one cannot be correct. Second one, it is always opposite in direction to the velocity. That is absolutely true. So essentially in this case, the damping is caused by the drag force, which is always opposite in direction to the velocity. And 3, it is maximum when the displacement is 0. That is absolutely correct, because when the displacement is 0, the force is actually the greatest, hence the acceleration is the greatest, and hence there's going to have to be an equal damping force to counteract that. So the correct answer has got to be B, no pun intended, only 2 and 3. Okay, so question 10. A trolley of mass M is put along a horizontal table by a force W provided by a mass hanging from the end of the string as shown. Frictional force are negligible. The acceleration of free fall is g. Which one is the correct equation for the acceleration of the trolley? So we have a trolley which has a mass m, and that's being pulled down along by a weight w. Just for completeness purposes, let's assume that the mass of this weight over here on the side, let's call that sort of lowercase m, and we know that w is equal to mg, so we immediately know that this little mass is going to be w over g, like so. Okay, well, let's find an expression for the correct equation of the acceleration. We're going to have to use Newton's second law over here. So Newton's second law suggests that the net force acting on an object is equal to the total mass multiplied by the acceleration of the system. Now this weight w here, though, that doesn't act on just one object, it acts on two. So the correct expression is going to be m plus m. So m plus lowercase m is equal to f. Well, we have to multiply that by the acceleration as well. Now the net force is w, so w is going to equal m plus m times a, so the acceleration is going to be w over m plus m. Now just one final step to add in, that will be w over m plus, rather than lowercase m, what I'm going to write down is what I did here, which is w over g, like so. So that's the correct expression for the acceleration, so that leads us to the correct answer being D. So question 11, we have some values over here of two wires x and y. We have the Young's modulus, of both wires, and we have the cross-sectional areas. What is the value of the ratio, the extension of x over the extension of y? Okay, well, because we're given the Young's modulus equation, the first thing to do would be just to find out an equation for the extension in terms of Young's modulus in the cross-sectional area. So I'm just going to do that on the side over here. I know that Young's modulus is stress over strain. So stress over strain. Now our stress is just the force over the cross-sectional area. Now strain is the extension over the original length. Just we can play around with this equation. In fact, what I'm going to do is I'm just going to rearrange for x. So all I need to do really to rearrange for x is to swap the Young's modulus with x. So x is going to be f over a divided by Young's modulus divided by L. Okay, and I'm just going to simplify the algebra a little bit. So this will also be equal to f, and rather than having divided by a here on top, what you can algebraically do is just put that on the bottom. So the area times Young's modulus, and if you're dividing by L, that means that you can bring this up over here. If you're unsure how it went from here to here, please write it out, or just leave a comment down below, and I'll be more than happy to explain this in a little bit more detail. Okay, so we have an expression for the extension x in general. Now remember, with ratios, what we need to do is just write the ratios out. So let's apply this for the extension of x. So the extension of x will be f times L divided by the area of x times the Young's modulus of x. And what we're going to do is we're going to divide that by the force applied on y, which is the same, multiplied by the length of y, which is also the same, divided by a y multiplied by Young's modulus of y. Okay, well, now we can do some cancellations, which is one of my favorite parts in physics. So let's do that with a red pen. We can cancel out the forces, we can cancel out the lengths as well, and we can start plugging in some numbers. So what we're left on the top is 1 over the area of x is just 1 times the Young's modular of x, which is 120, divided by 1, because I've cancelled everything out. The area of y is 2.0, and Young's modulus of the other material is 200. Now what I'm going to do is I'm just going to add some brackets over here just so that I don't forget to add those when I'm putting those into my calculator. So it's really important, but if I put this expression in my calculator, and want to make sure that I haven't confused the calculator, so I'm not going to get the wrong value. And if I put that into a calculator, I'm going to get approximately 3.3 recurring, so up to 2 significant figures, that's 3.3. Now a common question that I get is, why didn't I consider the units? For example, this over here is in giga, which is 10 to the 9, the cross-sectional area is in sort of millimeters squared, etc. The reason is because we're talking about a ratio. Over here the units will cancel out. So in other words, as long as both x and y are in sort of gigapascals, and the cross-sectional area, both the top and the bottom, are in millimeters squared, the ratio will remain unchanged. Okay folks, so hopefully that makes sense. Let's move on to the next one. Hey guys, so moving on to question number 12. An object is dropped from rest at time t is equal to 0. It falls vertically through the air. Which of the following statements is correct about this object? So A, it has constant acceleration. That is not true. In fact, we can see that the gradient of the tangent curve, which will give us the acceleration, is constantly changing. So it has quite a high acceleration to begin with. The acceleration is eventually reaching 0 as the curve tailors off here. So A is not correct. B, it experiences 0 drag at t is equal to 30 seconds. So at t is equal to 30 seconds, the acceleration is 0, but actually at this point the drag is equal to the weight. So they're fully balanced out, so there's definitely drag, and that's equal to the weight. B is not correct. C, it has an acceleration of 9.81 meters per second, which is the value of g at t is equal to 0 seconds. Yep, that is correct. The reason for that is at t is equal to 0, the object experiences that acceleration g, but no drag has developed, because drag is proportional, was proportional really to the speed squared. So if you're not moving, then there's no drag. So right at the instant when it's dropped, the object experiences an acceleration of 9.81. D, travels the same distance in every 10 seconds. Yeah, this is obviously not true as well. So the correct answer is C. Nearly there guys, question 13. The Earth has a mass of 6,724 and a radius of 6,400 kilometers. We're setting off a satellite. We have the mass of the satellite and the height of its orbit. What is the change in the gravitational potential energy of the satellite? Okay, well, let's say that the change is equal to your final potential energy minus the initial potential energy. The formula for potential energy is minus gmm over r. Let's say that at our height at an orbit it's r2 minus the potential energy on the surface of the Earth, which is minus gmm over r1, which is just the radius of the Earth. So this is going to equal, let's plug in some numbers. Minus g is minus 6.67 times 10 to the power of minus 11 multiplied by 6.0 times 10 to the power of 24 multiplied by the mass of the satellite, which is 320, divided by the height of the orbit, which is 6,400 plus 1,200 kilometers. So the result of that we're going to need to times by 10 to the 3. Now from that we're going to need to take away, i.e. add mathematically, because this these two minuses here are going to turn into a plus 6.67 times 10 to the power of minus 11, exactly the same expression over here, times the mass of the Earth, which is 6.0 times 10 to the power of 24 times 320, and then we're going to divide that by the value of just the radius of the Earth, which is 6,400, and we're going to need to times that by 10 to the 3. Okay, so let's put that into our scientific calculator. So after we've put that pretty long expression into our scientific calculator, we're going to get about 315947368, which is essentially B, which is 3.2 multiplied by 10 to the 9 joules. So the correct answer is C, excuse me, I think I said B a moment ago. So the correct answer is C. Okay, question 14. The volume of 1 mole of gas is V. Okay, so for 1 mole, we can just say that N is equal to 1. The gas exerts pressure P and it has temperature T. Which of the following has the unit joule per mole per Kelvin? Okay, well, let's write out our equation here. Our trusty PV is equal to nRT. Now, because what we're looking for has units of per mole per Kelvin, I suspect that we're going to be looking for is the base units of or the units of R. So let's just rearrange for R. Now R is going to be PV over T. And a factor of N over here. Because this is just 1 mole actually that we're dealing with, so R will be PV over sort of 1 mole times T. Okay, well, let's find out some base units in this case. Now pressure is just force over area, isn't it, multiplied by the volume divided by 1 mole in this case, multiplied by T. Okay, well, let's find out some units. So the force is measured in newtons and area is measured in meters squared, multiplied by volume, which is in meters cubed, like so, and we're going to divide that by obviously a mole times the temperature, which is measured in Kelvin. So if we combine some of the units up there, so those two are gonna cancel out, so this is going to cancel, and what we're going to be left with at the top is a Newton meter. So Newton meter, like so, and we're going to divide that by a mole and a Kelvin. If you haven't come across these brackets before, we just use them in physics just to denote the pure units of quantities. Okay, now if you remember though, 1 Newton meter is actually a joule, so Newton meter is actually a joule. Easiest way to remember that is that work done, which is measured in joules, is equal to force multiplied by distance. So a force is measured in newtons and distance is measured in meters. So 1 joule is actually equal to 1 Newton meter. So we can write this as a joule divided by a mole. So I can say that this is equal to mole raised to the power of -1, Kelvin raised to the power of -1 as well. So let me just carry on with my notation with the brackets. So we can see that joules per mole per Kelvin, PV over T has those units over 1 mole times T. So there's a little catch over here. There's a little 1 which might confuse quite a lot of people, and that 1 over here is the 1 mole of gas. So the correct answer is D. Okay, for question number 15, an object oscillates with simple harmonic motion. Which graph best shows the variation of its potential energy with distance from the equilibrium? Now we know that the variation of potential energy with respect to the x-axis, it kind of looks like this. So if I was to draw this, it will look like this, where this over here is your potential energy and this over here is x. So in this case, just that right hand quadrant is represented in the correct answer being B. We know that the potential energy increases with distance, and we also know that it's not a linear relationship. So it can't be A because A is linear. B, that's the correct answer. C, once again, this is not the correct shape. It doesn't increase in this way in particular. And for part D, the energy is decreasing. So both of those are not correct, and it's quite useful to just keep that graph sort of in memory for the actual exam. Okay folks, so hopefully you found this video quite useful. If there are any further questions, please feel free to drop a comment down below and consider subscribing for more.